We're going to start talking about neural network computation and then RNNs. Okay, so I think we have spent enough time talking about artificial neural networks as well as convolutional neural networks, right? We talked about a lot of details for this kind of grid data or image data. And I think through this process, we have already noticed a lot of things that we need to understand the details even more, including how it's done computationally, right? So we mentioned back propagation a lot of times, but I think it's very important to really understand them. And then, starting from Thursday, we'll start talking about sequence data or text data and the corresponding architecture that is a recurrent neural networks. Okay, I think we should include the language models next week because that's sort of the state of the art. And we'll include some case studies, okay? Okay, so what do we have learned last week? We talked about image data that is very special, right? 2D, 3D grids of pixels, and there is a very structured information. So apparently, using MLP is not utilizing the structure, and it's also a very expensive process, right? So what we learned was that we want to kind of, reduce or regularize the model, right? But we don't have ideas that just come from nowhere. The ideas actually came from how our, vision systems work, right? And we have learned about the locality. We learned about the equivariance of our vision systems. Then we decided that, these are the knowledge that can drive this model reduction relative to MLP, such as sparse interactions, parameter sharing, and equivariance to translations. Motivated by these desired properties, we introduce the corresponding mathematical operators, such as convolutions. We spend a lot of time talking about the fact that convolution actually cater to these desired properties, and actually it's much smarter than it appears, right? Remember how wide the receptive field can become when you increase the depth of the intermediate layers, right? We talked about the channels, how it can be very easily incorporated into the tensor calculations. We talked about the pooling. It's very similar to convolutions, right? It's local, but it's parameter free, right? We talked about strides that can control the resolution, right? Pooling that can control the image size, right? And then padding that can maintain that image size from one layer to the next layers. We talked about how much computations can be saved using one concrete examples, right? Using convolutions versus using MLPs. Those are examples what we have talked about. We also talked about what else can be done ever since convolutional neural networks or LaNet, right, or AlexNet later on. We have seen how the later models for computer vision have been developed. We have some summaries about GoogleNet or VGG and what are their contributions, or ResNet, right? So now I think it's time to talk about the computations and a little bit of theory behind these neural networks, right? In general, not just convolution, but neural networks in general. So a little bit of background, right? So remember we talked about at the beginning linear regression or other kind of simple neural networks, right? We said that you can look at them from the perspective of optimization, right? So you first have the data, right? The I/O relationships, right? And the examples of I/O relationships, and then you have the model, right? This model class is defined by MLP or CNN or other kind, right? More general than the linear classifier you have seen in the shallow machine learning models. So once the data and the models are determined, training the model is equal to solving an optimization problem, where the decision variables are model parameters, right? And the objective function or the cost function is the loss plus regularization, right? And the optimization algorithm or the optimizer is to find the optimal parameters, right? And I can give you the conclusion that they are dominated by gradient-based methods. We introduced the classical gradient-based methods before, right? A lot of, gradient descent, conjugate gradient, Newton, quasi-Newton, and limited memory BFGS, right? But we'll see how they should be changed or evolved in the case of big data, right? So now, first of all, I want to ask you the question, right? Why do you think that the deep neural networks or MLP would work, right? Let's talk about the model class, right? You think that your model class is adequate for the problems at hand. So how do you get that belief? So it comes from theory. So there are two approximation theorems for you to understand, right? So the first series of papers, 1989, stated the following universal approximation theorem, which says that a feed-forward network with a linear output layer and at least one hidden layer with any squashing activation function, such as the logistic sigmoid that you have seen before. Such feed-forward network can approximate any Borel measurable function. By Borel measurable, I mean any continuous function on a closed and bounded subset of an n-dimensional real space. Okay? So a feed-forward network like that can approximate any Borel measurable function from one finite dimensional space to another. Okay? With any desired non-zero amount of error. So, right, that's the conclusion. The condition is that to have that property is that provided that the network is given enough hidden units. Okay, so this is what the universal approximation theorem says, right? So it's about what kind of feed-forward network can approximate what kind of function to the zeroth order, right? That's the conclusion. And there's another version actually that can also talk about the first order information, that is the derivatives of the feed-forward network can also approximate the derivatives of the function arbitrarily well. That is a 1990 result. So these theoretical results for the zeroth order and the first order approximability shows that if you have a large MLP, they can represent the function of interest. You have to pay attention, okay? Because this is a universal approximation theorem which says that the MLP model is a model class that can represent the function of interest, like the Borel measurable function, right? It doesn't mean that MLP, you can train an LP and learn the function of interest precisely. I didn't say that, right? Right? Because in the end, it's determined by the data and the training algorithm, right? It's an algorithm that learn the function, right? The model class is covering or representing the function of interest, but in the end, you need to learn the function, and the optimizer have to operate on the loss function, minimize the loss function, given the data, and you have to consider, for instance, if there's a lack of convergence or kind of overfitting, then even though the model class is general enough to cover the function of interest, you may still not able to learn that function with your MLP, right? So that's something you have to pay attention to. One is representing and one is learning. So let's understand the universal approximator theorem a little bit more, right? And let's say one hidden layer is enough to represent, okay, not learn, an approximation of any function to an arbitrary degree of freedom, right? So because remember, the condition is that as long as there are enough hidden units, right? So then if I have one hidden layer, and then if I have many neurons in the hidden layer, that's called the width, then that's enough, right? But you have learned much better than that is deep neural network is really about the depths, right? 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 The magic comes from the depths. So if you can, have the same amount of hidden neurons using one or multiple layers, hidden layers, why do you prefer going with a deeper neural network or more hidden layers? Apparently I wrote something, but what is your understanding? What's a big deal about the depths? Any try? Pardon me?
Is it for learning because it just represents what I'm not sure.
Okay, good point. You are saying that maybe it's same amount of representability, but it's easier for learning. Is that right? That is a good point. I think, is it easier for learning? I'd say the depths actually brought in more challenge to optimization. But could it be still benefiting learning in some way? That's a good point. Let me think about it a little bit more. And my argument is that I think you're looking at the right perspective. You're looking at the representation and the learning, right? But you seem to have assumed that, as long as there are the same amount of hidden neurons, then there is the same level of representability or expressiveness of these two MLPs. In fact, that's not the case that you can get a better representation. Okay, let me put it this way, okay? These theoretical results are like the convergence proof that we have seen before, which is an asymptotic result, saying that when the samples go to infinity or when, the number of hidden layers is large enough, right? So in reality, of course, we never have that. We always have, a small or, medium finite number of the hidden units, right? So I'd like to put in this way that, the width and the depths affect the expressiveness of the model differently, right? One is like, in the base, and one is like in the exponential term, if you get what I mean. Okay, I will show you with illustration next page, okay? But a simple quick points are first, right? If you have a shallow network, then you need more width, more neurons. But, to compensate a loss of a layer, you have to use exponentially more width. In other words, width and the depths affect the expressiveness of the model differently, okay? And you will see right away why depths is more like the exponential term, because you are composing, layers after layers. We'll see that, intuitively next slide. And secondly, the shallow network may overfit more. Okay, so does anyone have any doubt about my second claim? So please don't take them as conclusions, right? I know some people say that tuning machine learning or especially deep learning models during training sometimes, is very empirical recipe based. But here, I think we do have very deep theoretical reasons, okay? We'll talk about overfitting in a few slides, but let me show you this deeper network, right? the exponential representation advantage of depths, right? So now let's look at a very concrete example. Right, this is like a two-dimensional space where we have blue versus red samples, right? Our goal is to design a classifier that can separate the two, right? So apparently, well, for some reason, let me see if I use it, show it a smaller, interesting. So it appears that, I just copied a figure, but something in the figure is missing. So let me see whether I can draw in the figure. Okay, so let me see whether I can draw in the figure, okay? So apparently the ideal classifier, right, is something like, okay, right? So this is, in the original domain, right? So let's, so this is, it's, in this case, right? So this is, decision boundary, right, in the two-dimensional space, right? So now let's see what the depths can do to you. It's like folding, right? Remember I said before, the key of deep neural network works, right, using so many linear layers followed by activation and composing the linear layers is really to decompose a high-dimensional manifold, right, into piecewise flat facet, right? The key is really like, the reason is that when you compose layers after layers, it's like you're folding this paper or, doing this piecewise flat approximation. So now imagine that, right? So now imagine that, when I try to get this function, right? This is the function that I want to learn, represent and learn, right? So apparently, you can see that these, I want to learn this sophisticated function, right? By aggregating or composing simple functions. So one thing I noticed is that this function, for instance, is like a symmetric, right, along this axis. So if I fold my paper along this symmetry axis to the right, so this is where I fold, right? Then you realize that in this new space, I just have to learn this simpler function. Right? So this function can be obtained by folding the space around the axis of a symmetry, right? And then I observe a local symmetry here again. So then I fold again, to the left, right, along this axis of symmetry, and then I end up having this, right? And then in the end, if I keep folding, right, I have a way simpler function, right? So remember, by folding the papers, what I'm doing is actually trying to see how sequential folding, right, can reduce a complex function into a very simple function in one, in this final fold. If I go backward, it's equal or equivalent to ask, how can I start with a simple function, right, like represented by a layer, right? Single layer perceptron followed by activation function, nonlinear, right? So you can think of this function as a single layer function. Then, if I keep, right, if I keep composing additional layers, then in the paper it's like, I'm expanding to these more and more complicated functions, right? So this shows the power of the depths, because the depths is the number of times you fold. And then apparently, right, if you look at here, we fold two times, then we are basically having approximation of a function with kind of one global and another local symmetry. So this kind of complexity. But if we keep folding, right, then we see that that is something like the exponential, right, 2 to the power of the depths that we can cover the complexity. So this shows this exponential representation advantage of the depths, right? Any question about this visualization? Is it clear to you? The relationship between paper folding and composing linear, not necessarily linear, but composing the hidden layers. Okay, so this is about the model class, why we believe that DNN, especially MLP, can approximate, right? And then why the depths matter, right? And about the second claim I had, that with greater depths you have a better generalization, right? So this is some figures that looking at the test accuracy versus the layers, right? So if we look at the other end, that are large but shallow models, right? So if we look at this one, right? So let's look at the number of parameters versus the test accuracy, right? So this is post hoc assessed. So we have the fully connected MLP, right? That is 3-layer, right? So they tend to have a lot of parameters, right? So more to the right. Then for the same depth, 3-layer convolutional neural networks, we have much less parameters, right, compared to the green. And then with roughly the same number of parameters, we can afford having much deeper convolutional neural networks, because convolutional neural networks have sparse interactions and parameter sharing, right? So if you look at the outcome of the test accuracy, right? So of course, this is something that you don't know a priori, right? This is like the bias variance trade-off that you observe in the post hoc assessment, but to find the sweet spot, right, you have to use cross-validation, right? So here you see that apparently, the shallow convolutional neural networks compared to the deep convolutional neural networks, you see their performance difference, right? And the large shallow models, tend to overfit, right? Right? So besides the model class, right, the second thing we should look at from the perspective of optimization is the loss function, right? So the loss function we have learned a lot before. For instance, we learned we can maximize the log likelihood, right? And we can maximize or minimize the mean squared error, right, depending on what kind of task, right? Here I want to talk about the choice of the loss function, right, tied to the kind of the predictions you want to make and the desired output distribution and the choice of the output layer, okay? So for instance, if you are trying to model a Bernoulli distribution, that basically the output is binary, right? 0 or 1, right? And in the output layer, we usually use a softmax, right? Which is giving the probability of p and 1 minus p for the two classes. And the cost function you usually use is a binary cross entropy, right? Remember this question I asked before, right? And it's essentially a minus log likelihood, right? In the case of the multiple classes, it's a not Bernoulli but multi-Bernoulli distribution, right? So your output is not like a binary but multiple discrete choices. But then you have a softmax again, right? And then in this case, you have the generalized cross entropy. That's not for binary, but for the general cases, okay? So now if your labels or the output type is continuous, right? And the distribution is kind of like a Gaussian, right? And your output layer is linear, right? Then you can prove that this, cross entropy, in this case, a Gaussian cross entropy, is essentially the, mean squared error, right? That you usually use. But if the continuous output has a desired distribution, which is like a mixture of Gaussian, right? So the output layer is giving you the mixture density, then the cross function is cross entropy again, right? And then if you have other kind of assumptions, right? Including the output distribution, and you have different kind of output layer, then your cost function will be, dependent on the choices. The cost functions are very different, right? So if you want to look into more details, you can look into the deep learning book, whose electronic version is available online, right? So it's in the chapter 6, right? So I think you should be, some of you should know, right, what is the cost function in generative adversarial networks. Anyone? What is the cost function? Okay, we'll talk about them again in the close to the final weeks, okay? But I think you should know about them. But one thing I want to emphasize here is that you haven't learned a lot of isolated knowledge points. I'm pretty sure. But here I hope that I can thread them together in a systematic way so that you can see those seemingly disparate or isolated knowledge points better. In other words, understanding them better, okay? So here, for instance, if you think about the choice of the cost function, together with the output layer and the output distribution, output type, you have a much better understanding than just trying to accept them as they are, okay? Okay, so then in the last function, remember, we talked about the regularization before, right? So in the shallow machine learning model, we try to have a better generalization error. And one way to achieve that, according to the bias variance trade-off, is to sacrifice the bias a little bit by making your model less complex. And the hope is that the variance part gets reduced much more. So the sum, right, gets lower. That's for the generalization error. So that effort is called a regularization, right? So how you regularize your model complexity, we said before, model complexity cannot be easily estimated just by the number of parameters alone because it's data dependent, right? One way is actually to use the LP regularization, that is to use the LP norm of the parameter weight vector, right? And you see that by regularizing the length or the size of the parameter weight vector, you can regularize the model complexity, right? In neural networks, you can still include L1, L2, or LP norm, right? In your loss function, that you can still do that. But you can do more than that. Why? Because your parameters W, right, are now structured. What do I mean? You have some W's belonging to the first hidden layer. You have some parameters belonging to the second hidden layer, and so on. Right? So this, some parameters belong to this, linear, the W, some belong to the activation function. So in other words, your parameters are very structured. So you can actually use additional regularization approaches, right? Besides simply L1 norm. One way is drop out, right? Because the parameters, in our cases, are very often related or associated with the interconnections between the neighboring layers neurons, right? So if we can reduce such interactions, then we can reduce the number of parameters, right? So the dropout is basically, sometimes we call it a dropout layer after the fully connected. That is, you will remove some percentage of the random nodes at each training iteration. And this is random, okay? So you are dropping out some percentage of random nodes, and of course their associated interactions and the parameters wi's. This is random, okay? And this is done at each training iteration. The nature of this method is actually essentially equivalent to an ensemble method that can reduce the variance. Okay, so that's why dropout would work. Another thing is when you're doing the training, you can do early stopping, right? So you can save checkpoints during the training and choose the best according to the validation instead of choosing the last or the ones close to the saturation or convergent. This early stopping can also prevent you from overfitting, right? And lastly, you can always try to provide more data. So we talked about bootstrapping, right? The approach of bootstrapping in the case of shallow models, right? In the deep models, you can do more, partly because we are not telling some properties of the desired functions directly to the neural network model class. For instance, in computer vision, we know that for the object detection, right, or labeling of the image, these pixels belong to the cat, right? We don't care about where they are, right? Whether they are rotated, translated, or rescaled, right? The label would remain the same, right? But our convolutional neural networks is only equivalent to the translation, right? Because we are using the CNNs, which are like local filters that are glanced through, right? But it's not invariant to the rotations or scaling. So in computer vision, it becomes a must that if you have an image, right, you have to randomly rotate them in multiple copies and give all of them to the model training. This is a way to tell the model that this model should be relatively invariant to the rotations, but it's a very indirect way, right? So this is called a data augmentation. So there's no general recipe. It's a way to try to mimic the real world variations. Okay, so these are the loss function, right? About what kind of loss function, what kind of regularization we really have to choose.